Hi, good morning, everybody. My name's Richard. I'll be taking you through this first session for the first hour of this morning. Then we're going to hand over to Hans to take some questions and answers from everyone later on. So, like I say, my name's Richard. I work at the University of Salford. That's in Manchester, in the northwest of England, and I'm a reader in energy performance of buildings. So we're going to look at a few different concepts today. It's going to be quite a broad discussion around several different components of energy, more or less around the concepts of energy performance of buildings. Hopefully you'll find it useful. Hopefully there's some useful things in there for you to get a grip on. Well, and we'll take any questions at the end. So we've got a Q&A session right at the end. So just bear with me. So the aims and objectives for today really are to look at the following topics: that why we measure buildings, or why we measure the energy performance of buildings. Just a brief look at that. There's a lot to discuss there if you want to take it into detail. We're going to look at smart meters, context, their capabilities and their limits. We're going to look at some examples of how we use smart meter data and in tandem with energy performance work. I think a question that everyone asks is, how do we get hold of the data? I'll try and answer some of those questions, but that's quite a varied task as well. And then I'll try and wrap it up, and we'll take any questions right at the end of the session. So just a little bit about me. So like I say, I work at the University of Salford. We in the Energy House Labs team. These are the things that we look at generally: energy consumption in the home, and some small commercial work as well. But generally, it's domestic. We look at how the energy system's changing, so decarbonisation, decentralisation, and important to this session is digitisation. We run the full gambit from insulation to heating systems, controls, smart meters, EVs, and everything in between. So anything you can really add to a domestic dwelling to either make it more carbon efficient, more smart, more easy to control, or more comfortable. And the final point there is really quite important for what we're discussing today. Domestic energy is getting really complicated, and we think it's going to get even more complicated as the years go by. So this is why our Energy Labs research group kind of has taken this approach. So these are the models that we use to work to. So it's a really simple consumer. Gas or electric goes into the building, and that's really it. Okay, we measure the gas that goes in, we measure the electric that goes in. At a push, we might look at PV. So if you take that back 10 or 15 years ago, these were the models that we were currently working with. And that's what we would call a simple consumer. It's not happening like this now. This is now classed as probably a new model, and even this is probably quite a simple setup now for a lot of consumers. So electricity is going both ways. We've got rid of gas, as you'll notice. So I can always speak with any intelligence on the UK situation, but our aim is to get rid of gas installations altogether by the year 2025 in the new buildings and any significant retrofits that are done. So that will go. In the 2030s, we're discussing the prospect of not replacing gas boilers, so taking those out as well in replacement installations. But this picture of electricity flowing both ways is now real, and it happens. So, vehicle to grid can happen between vehicle to house, vehicle to grid. It can push both ways. We've got the smart meter installs. We've got the PVs. We've got batteries. You can add to that things like air source heat pumps, ground source heat pumps, infrared heating, and anywhere in between. So this idea of that being the old model and this being the new model has actually now come to life. And hopefully regulations across the EU and across the UK will lead us further down this track. So that's where we're heading as a research group. Hopefully that's where we're all heading globally, and certainly as a country in the UK. So we basically look at this through a series of different lenses. So these are our labs. So we have the Energy House, which is a Victorian terrace in a very large environmental chamber. We can reduce the temperature -12 up to +30, put wind, rain, snow on the building, things like this. So we can look at how we make changes to that building and how it affects the energy consumption. Thermal laboratory, that's very much about the products that is involved to improve our buildings in terms of energy efficiency. And that is exactly as it is laid out there. It's how we measure the thermal performance of insulation materials. Then we have our smart meters and smart homes lab, which is part of this discussion. So that's how we get data, use data, and feedback data from the smart meter installs that are going on. And then we have our new project, which is Energy House 2, which is focused entirely on the decarbonisation of the newer buildings that we're putting in across the globe. And that should be finished in a couple of months' time, actually, December this year. So that's what it looks like in a digital model. So there's enough room in there for 4 homes. This is what it's currently looking like under construction. And these are the people that we work with. So a series of academics, researchers, and support staff. So we're a fairly kind of tight team. Like I said, Energy House is looking at retrofit. Thermal measurement is looking at how buildings, the material we use in buildings performs. And the smart meters, smart homes lab is probably what we're going to talk about most today. So that's me. I'm the technical director of those labs. So on to today. So that was just a bit of an introduction. We'll get that out of the way. So the context that we currently sit in, we have this well-documented phenomena, if you like, called the performance gap. So this is the difference between how we model buildings and how they perform in a real-world scenario. So there's just a selection of studies there. You know, it's quite small text. I don't expect you to be able to write all this down. The slides will be with you. But there's a series of work there that's been carried out by academics that basically say, look, there is a performance gap ranging from anywhere between 11 to kind of 74%. They're all measured in different ways. I would caveat that with, but nonetheless, it goes some way to saying that even on a small sample or a large sample, we get some differences between what we measure in the field and how we model buildings. The interesting thing is that we can find it on the positive or negative side of the model value. Many pieces of research are finding it on the negative. So our models say the buildings are better than, are performing worse than the models are. So we try to find out why, and that's actually incredibly difficult. So, you know, as I put there, many researchers have tried to state why. It's usually an amalgamation of several different reasons. Maybe it's modeling hasn't been done quite correctly. Maybe it's the workmanship that's maybe lesser quality than it should be, but any other reasons as well. So the default value could have been entered into an energy model that wasn't included in the actual building. So we need some ideas of how we can measure the building rather than just simply model it. If we are to roll out large-scale retrofit and large-scale regulation on new builds to reduce our carbon, which I believe we should, then, you know, these are things that we need to look at. So we need to dig a little bit deeper. So the way that we model may not be perfect. I think everyone can admit that. A lot of the models that we work with in the UK, for instance, are steady state. So they don't take into account the dynamics in the system. We should always see models as a simplification. It's not the actual building. If we want an idea of how a building performs, we have to build it. That we can't computer model everything. It's as simple as that. Then particularly when we do the obvious thing of put occupants in the building, and they all start to live in this building in an entirely different way. Many people will criticise a model after analysing the results from a poorly measured campaign. So we talk about measurement of building, measurement of energy performance. I've seen and other people have seen studies that have been done in different ways than we expect, with the accuracy that isn't there. Of it are designed to be an actual version of reality, and then we might criticize them against some poorly measured campaigns as well. So there is that, you know, and we can explain some of the performance gap for what we might call the measurement gap. So we need to always be conscious of that. So indicated very sticky and messy place to be, the performance gap. The definite answer. There is no definite tools to do this. And sometimes people want to ignore the performance gap. Sometimes people want to embrace it. But what people want to do most of all is when they find a performance gap, try and fix it and understand it. Okay, so one of the ways of doing this is to take a large sample of properties and maybe get a larger view. Now, the way to do this, in my opinion, might be to use things like smart meters and IoT and things like this to help address the larger picture, should we say. So how can smart meters help? So for anyone who's been in this area a long time, we will have seen things like this going on, which is basically a gas meter on the left, an electric meter on the right, and a data logger underneath. And what we do is we turn up to a building, we look in the meter cupboard or under the kitchen sink or wherever the water meter or something might be, something that we want to look at, and we stick things to the front of meters. So all these things do, they're optical meter readers generally, they are magnetic, so they will generally watch for something turning round, they will wait for a magnetic click, or they will wait for an LED to flash. And they will hour to it, or a litre to it, or meters cubed if it's water, or you know, you can see how old this meter is that we're working with on the left, because we're working in cubic feet. So these are very old meters, and we're trying to address them literally by sticking things on the front of them. And I've been involved in field trials right up until the current day, where we're having to do that when smart meter isn't in place, or it's talking to us, or something similar. So that's really the current situation for a number of people. We are sticking things with front of meters, which is not a good thing to do, I don't think. So historically, that's where we're at. But in 2021, should we be gluing sensors onto the front of gas and electric meters? No is the answer. And they do some odd things. So they fall off. Occupants take them off. When the meter reading people come, they take them off. When sunlight shines on them, they don't work properly and things like that. So, and it's also very, very expensive. So the logger that I showed you on the last page is about €1,600 or something similar. The meter readers themselves, probably now about €90 each. So not even a cheap way to do it. It's expensive. It can be inaccurate, and it's, I think it's safe to say that it's very very cumbersome. So how can we do things in a slightly smarter way? Let's have a look at some of the alternatives. So that's just another picture there of a gas meter that's had a similar kind of thing added to it. So first of all, what is a smart meter? So this gets quite confusing, because as you know, I think probably a lot of us on the call will be from the EU, and we like to think that harmonisation was a big part of the EU project. But the smart meter harmonisation didn't kind of come to pass in that way, and each member state was left to devolve their own way of doing smart metering. So there isn't one fits-all solution, one size fits all solution, and there's not even a common description. the European Smart Meter Association give us these following bullet points that may suggest what a smart meter is. And smart meters don't just include, gas and electric. They're for water and oil and things like this as well. So these would, if we take a broad view across the EU, this is what should be in place if it's a smart meter. Automatic processing, transfer, management of metering data. So everything's automatic. Nothing has to happen. No one has to dial into it. Automatic management of meters. So we can see when things are failing. Two-way comms. So we should be able to send things like tariffs and rates and error messages and shut down, things like that to the meter. Provide meaningful and timely consumer consumption information. So they should get some useful information, maybe by the hour, by the half hour, something like that. And that should be provided to the energy consumer and the relevant actors. So that might be the supplier, it might be the network operator, etc., etc. And it supports services that improve the energy efficiency of energy consumption. So that's quite a broad statement there. But things may be like a display that goes into the house, or a way that the consumer can view the data. It can be used on multiple utilities. So gas, water, electric, etc., and 1 meter for each. So it's saying that there is some description, and that's roughly what we're talking about across the states of the EU and the UK as well. So what do they look like? So this is a couple taken from our labs. So we've got on the top right there's an Elster one, which is kind of more of a building level smart meter, and that's got an optical output on it, but it also talks via 3G to the web and to a platform that we can view, and obviously to the supplier so they can bill us. The top left picture there is showing just a simple 1, 2, 3 pictures there of the smart meters that you might expect to see in a UK home at the moment. So that's on the electric side. And the bottom left and the bottom right are a couple of gas smart meters that you may expect to see in the UK. And also across the EU, I've seen a couple of these types of devices installed far further afield than the UK. So the main discussion there is they come in all different shapes and sizes, all different flavors, and some will talk to things and some will not. And that is a big battle for anyone working in this field, is to find out where you can get the information, how you can get it, and what you need to do. And it is different across every state, and maybe even different parts of each country as well may have different regulations and different rollouts of different kind of meters as well. So the key point there is it's not as straightforward as saying I can get smart meter data. It varies all around the globe. So there is no harmonization, but there is the aim. And so this is taken straight from the EU policy document. So it's an aim of the EU to introduce smart meters across the union at a rapid rate, with the aim of 72% coverage for electric and 40% for gas. And this looks like it's on track. Unfortunately, the smart meter statistics across the EU, certainly the ones that I've found, and I've tried getting several different sources recently, are quite old. So this next diagram basically tells us where people are at in terms of the EU states on their rollout process, if you like. So we've got some front runners at the top right. We've got some ambiguous movers, as they're called. We've got some people who are wavering on the edge, not sure kind of what they're doing or where they're going quite yet. Now, this was done in 2016, so I'm hugely caveating this slide. But it does paint a picture that some countries are very advanced. The EU average there, the orange dot, is still quite advanced, but we've got some people who aren't kind of doing it as quickly as the others, it's safe to say. But on the whole, there's quite a lot of people in that top right box, which is good for us as researchers and people in this area, because what it does mean is the fact that, you know, we're getting there, we're making some progress. So that's good to hear. It'd be nice if the statistics were a bit more up to date across the EU, but unfortunately they're not. So this is taken from the same report. So this is looking at the difference here between the electric rollout and the next slide, which is the gas rollout. So it's fair to say that the electric rollout is far more advanced than gas. And it's also fair to say that there's quite a big difference between each country's rollout plans. Some are very quick, some are very slow, some are well on track, and some are not. So it's really down to you as individuals and researchers to kind of get a grip of where your current where the country that you're working in is at in terms of the rollout. I can only speak for the UK. So in the UK, we're about, it's safe to say, about halfway through our rollout in terms of small commercial properties and homes. COVID gave us a huge setback, as I'm sure it did everywhere in the globe. But we are back on track now in terms of our rollout and installation plans. So there is the hope to be completed in the next 5 years, which I think might be quite a feat. So again, this is the progress with gas. Now, a lot of people aren't doing gas. You know, you'll notice there's less states on that graph than there is on this graph, and that's because not everyone is going to do gas. As I mentioned earlier, gas may not be the fuel of the future. I'm certain that electric will be quite dominant in most of the work that we're all looking at in the next 10 to 15 years. So maybe gas isn't such a concern, but if we're looking at retrofit properties and modernizing the older stock, then it is a concern. But again, it's down to you guys as researchers to kind of get a grip of where you're up to, or where your country is up to in this whole process of rolling out. So what can they do? This is another area that wasn't harmonized. And the variance is huge. It's really big. So for instance, if you look at an installation in the UK, we have a variance there. We can either plug a device into it or connect a device that allows for 10-second reads on electric, or we can rely on the national network infrastructure that gives us 30-minute reads. But that, if you look at that across the EU, that goes right up to 60 minutes for electricity. So we've got immediately there a variance across the states of anywhere between 10 seconds, which is practically real time in a lot of people's minds, right the way through to 60 minutes. So if you're looking at doing things like appliance identification, disaggregation of electricity loads, and smart things with energy, there's a lot you can do with 10 seconds, and there's probably a lot less you can do with 60 minutes. It's not to say you can't do anything with 60 minutes, but people would see far greater scope to work with the 10-second data. So we need to be conscious of what's available in our country as well, and what the current state of play with accessing that data is. There's also this whole idea of when the data is available. So it might be day +1. So it could be, for instance, that you can get 30-minute reads, but you can only get it the day after that event has happened. So there's lots of different ways of looking at that. Gas is practically always less. The electric meter is supplied, as you would imagine, by the electric that comes into the home. So that's got its own supply. Now that has to be limited. They can't use a great deal of power in that unit because someone's got to pay for it. But in general terms, it's never going to be short of power. The gas meter, so the gas meter in my house, for instance, is over the house, and it's in the garage, and that is powered by quite a chunky battery that sits inside the unit, and they usually last for 10 years, those batteries. And the reason they last so long is because they only wake up and send data about every 30 minutes. So it's called a sleepy device. It only wakes up and sends something either when it's asked to distinctly, or when it wants to, basically. So again, there's differences in the technology there, and I think hopefully you've picked up on this. It's quite obvious, but every country has very specific needs, very specific types of meters, and it will have very specific data. So the data that you can work with in the UK, for instance, might be on a totally different level than the data you can work with in, I don't know, maybe Bulgaria or something that's maybe not that far down the track. So it is difficult to understand until you dig deep into your own country's infrastructure. And that's something that you'll have to do at some point. So we can do lots with smart energy data, and we'll talk about those projects in a little while. But there's nothing that you can do at all, in my opinion, without taking another chunk of data, which is about how the building operates, temperatures, climate outside, and maybe looking at things like layers of occupancy and how that, let's say, affects the building's performance, or certainly building's consumption of energy. So we know they can generate accurate energy rating, accurate energy data, but can they generate accurate energy ratings on their own? I don't believe that that's possible without some other chunks of data. So for energy efficiency works and energy performance works, without going into a massive amount of detail, we need some inside and outside temperature as a bare minimum. We need to know why the building is using a lot of gas. Is it because it's cold outside, or is it because it's hot inside, or is it a mixture of the two? And we need to get this idea of the difference between the two climates, inside and out. So we can get the smart meter data quite easily. Well, we say that, but it's possible to get smart meter data. So we need something similar on the inside and the outside of the building. And I believe here that IoT is the way forward here. And when I say IoT, it's anything really that talks to something outside the house. So the Internet of Things, we basically describe by something that sits in somewhere and talks to somewhere else, whether it's a cloud service, whether it's a server, whatever that turns out to be. And we're certainly not going to go into detail about that. But there are lots of them about, and they're increasing in number every day. Again, I've got some statistics in this deck of slides that are quite hard to get hold of, and they're in papers that I hadn't read before, but they're also quite dated. And I think you'll be quite surprised at the large numbers of devices that are out there. So just to kind of wrap something around smart devices, these are really things that we're talking about. So smart thermostats, again, in an ideal world, there would be a definition of a smart thermostat. And believe it or not, I've sat in a meeting before now where we've argued for an hour and a half about what a smart thermostat is. Not a good use of time, but it's proof that not everyone agrees with everyone else about what something smart is. So this is a definition. I think the best definition I've seen. So a smart thermostat communicates with other devices via the internet or wireless. It allows the user to remotely monitor and control via an in-home display, computer or mobile. So you can talk to it through a different interface. Detects the home occupancy and adjusts the heating cooling system. That's one that someone might disagree with. Smart thermostat can send notifications if there's a problem with your heating, and they can automatically learn to optimize based on your habits, preferences and conditions in the home. And clearly it allows the user or the occupant to set up a schedule of time and temperature and things like that in the home. And they can vary anything from something like Nest, which does it on a room by room level, to Honeywell, the Evo Home, which does it on Nest does it on a building level, Evo Home does it on a room by room level. There's lots of different ways of looking at that data. So, and we'll talk about that in a few minutes. So in terms of how many are out there, so this is a paper from both of these papers, and it was a market research report as well at the bottom, was done in 2018. Now, we did have a slowdown the last 18 months. So these figures might not be hugely wrong, but I think we can safely say that they're an underestimation of what's currently in place now. So actual sales figures are difficult to come by. So Shin and company basically estimated that the smart home technology is currently in about 7.5% of homes globally, with an annual market of 44.2 million. Now that must have changed by now, and it's going to be far higher, and that market value is certainly higher. But this is quite interesting that the EU is a strong leader. So the EU in 2018 had 10% of households with smart devices in them. So smart thermostats, IoT-based thermostats, if you will. So again, 2018, it must have changed by now. So a total guess might be 15% or something similar, but again, that's a guess, not a piece of research. The point is that these are very, very growing markets, and they're accelerating rapidly. And given that we're all pretty aware of gas prices in the last few weeks, I think it's safe to say that many people will be investing in devices that can help save energy. So that's just something to keep our eye on. So we talked about smart meters and how they may be rolled out across the EU and other states and other parts of the world as well. Many countries, that's their intention. So we can do some stuff with the smart meter data. It's also safe to say, I think, that the smart devices will be ubiquitous in, let's say, 5 or 10 years. I think we'll see a heck of a lot more of them. So if we start to look at how we group those together, then we can see that there's some projects being done recently with some quite interesting findings. So there's 2 projects that, and I'm not going to discuss these at length because I'm going to point you to some resources that do that, and you can sit and watch the workshops and you can read the reports. But there's been a couple of high-profile projects that's looked at smart meter data and onboard data. So onboard data is what we refer to as IoT, something that we don't have to kind of stick things on things to. So we can talk directly to thermostats, we can get remote sensing and things like this. So the Annex 71, so that was International Energy Agency Annex 71. There's a web link there. The slides will be available after, so you'll have access to these links. And that was a big project. I'll talk about that in a second. And the SMETRS was a UK-centric one, but it had some actually very interesting findings, and certainly findings that could be relevant to whatever country was looking at this report. So the Annex 71, we had the final meeting of the Annex 71 a couple of weeks back, and it's probably my fault, but it's took quite a long time for the videos to go up. They are up now and they're on YouTube. So you can, so there's a playlist of all the presentations. So all Annex 71, well, certainly 70% of Annex 71 was dealing with what we're talking about here. So it would be wrong for me to just run through a set of slides about Annex 71. You can find out everything that you need to know by looking at the link on the previous slide or the YouTube event here. When it was a very good event, some very high profile presenters and some very good discussion and dissemination there. So I'd encourage you probably to have a look at that as a first port of call if you're interested in doing this type of work, no matter where you are. So that was pan-EU, and that was all across the EU. So do have a look at that. SMETR, so the SMETR project had an online workshop that's very relevant to today's session. I would advise that you take a look at that because that was all about why we do it, how we could do it in the future, maybe some of the disadvantages of doing this and how we can improve some of those. But it's a very good starting point to what you should be looking at in this area, I think. So the reports from both of these projects were very encouraging. It's wrong to say that we answered all the questions, and it's wrong to say that there aren't a lot more questions to be asked. But they did come across to put it in a big picture context in a way that we should be carrying this work on. There is lots of scope for improvement, but there's lots of scope for doing further work on it as well. And there's lots of uses for the data that we can get out of it. So when we get this energy performance figure for a building, it becomes a very, very useful thing for all manner of different work streams, whether you're sizing heat pumps, whether you're doing retrofit, whether you're validating the performance of a new build, whether you're doing carbon accounting across a city region, that there's dozens of different uses. So it's all good. And you can probably hear by my tone that this is kind of what I like to do. This is my area of research. But how do we get it? And this is the tricky point. And it's highly country and supplier specific. But many suppliers will have an interface to the data using a cloud platform. And what we usually mean by a cloud platform is an API, so an application program interface. So what, in basic non-computer terms, it lets two things talk to each other, and it's usually two pieces of software talk to each other. So that's basically one computer running a bit of software talking to another computer running a different bit of software. And generally how that works is our computer asking a cloud service for some energy data in this. So it's, you know, it may seem complicated, but it genuinely isn't. So we work in partnership with a provider called Octopus Energy, based in the UK. They are a leader in innovation, I think it's safe to say, in the energy sector in the UK. And they do a lot of innovation around smart meters, EVs, vehicle to grid, batteries, solar. They do a lot of the kind of, let's call it, new stuff. So they provide a REST API. So that's basically a very basic interface for customers and partners to interact with their platform. So this is taken straight from their website. It allows you to browse energy products, tariffs and charges, UK electricity meter points you can get off from there. You can browse the half-hourly consumption for an electric or gas meter. That's where we're at. That's what we want to be talking about today. We can create a quote. We can create an account. Basically, it's their way in to their system. But we're really interested in that fourth bullet point from the bottom. Browse the half-hourly consumption of an electricity or gas meter. So that's where we want to be. That's where we want to be looking. So I'm just going to run through an example. So this is, I haven't done this. So Yanis Paraskevas and Dynastea from our research group in smart meters and the smart homes lab has just put together a very brief walkthrough. And I asked Yanis just to do a screen capture of it, just to show that it's quite a straightforward process. For the non-IT people on the call, this is using a piece of software called Postman, which is free. The idea here isn't to show you how to get smart meter data. It's just to show you that there is a process and what it might look like as well. So I'm just going to go to the next slide. There's no sound on this, so I'll kind of do a little voiceover for what it's worth. So hopefully this should just play. So basically, I know you can't read the text here. I don't expect you to, but we basically send a request to the Octopus server. That comes back in a format called JSON. So that's like a database kind of format. Then Yanis just very quickly, for the sake of this presentation, puts it into an online conversion tool. And now we start to see something that would look a bit more realistic to us all. So these are the consumption figures here, and these are the intervals here. So the dates and the times. And you notice here that they're at half-hour intervals. So all he does then is he saves it, he drops it quickly into Excel. Then he does a little bit of tinkering in Excel to basically, they always come off in the wrong order. So they always come off in the oldest reading first, which we don't want. So we swap that round. We can see here that column D is the one we're interested in. So this is the the energy consumption for each half-hour interval. And now it just puts it onto a quick graph, which is what we should all do. We should all get used to graphing information just to get a look at the information and make sure it makes sense. So this is taken from our smart meter lab, so there's not a great deal of consumption. There's only a few appliances that are kind of going up and down. And then you'll see him just looking at the axes here. He'll change that. And then what he will do in a second is he will change the axis at the bottom to give us time and date. So it makes a little bit more sense. Second. So we just edit that. We tell it to use this field here as the time and date, and then we okay that, and then we should have a nicely formed graph here. So this graph now plots across, I think it's 2 days of the electricity consumption. So it's a fairly basic series of steps. all we do is we query a database using a software tool. We tell it which dates and times that we want from point A to point B. It gives us a file, and we extract that and we put it into a format that we can quite easily read. So there's nothing more to it than that. Now, that's quite a long and elaborate way of doing it. How we usually do it, it's a little bit more of a grey box, is that we get the computers to talk to each other, and it basically downloads the data every night, puts into our database, and then we can use it for our research. That's just a basic presentation there to show that you can do it by hand, you can do it by property, you can do it by meter, but clearly we wouldn't do that on a large field trial. We would have all that data being posted into us on a regular kind of basis. So just go through that. So if you want any sample smart meter or JSON files, then just drop me an email. My email's there, and it'll be on the presentation notes as well. So in terms of smart, and it's exactly the same process for the gas meter inside of things as well. So you can get 30-minute data from that similar system. So that's great. The smart meter data, okay, we got that in the bag, but we can't really do a great deal with it if we're looking at heat loss and heat transfer coefficients, unless we have this delta component. So we need this difference between inside and outside temperature. So I've put together just a couple of systems that I've worked with in the past. So for instance, TADO is widely available across the globe now. So TADO don't have their own interface as such, but OpenHab, who are a group of people who kind of hack their way around things to kind of get smart home systems working. They have a binding mechanism for TADO, so you can download the data from either the room thermostats, the TRVs, or the heating patterns themselves. So that's useful for grabbing internal data from homes that have got this type of system in. Honeywell Evo Home is quite notorious around the globe, actually. It's got a large footprint. They have a very well published and documented API. So you can pull things like set points, which is interesting. You can pull obviously the room temperature, and you can start to look at the consumption as well in terms of when the gas is firing. So that might help you look at things like occupancy patterns as well in buildings. People tend to heat the buildings when they're in, particularly if they've got a system as advanced as this. So you can start to look at inferring different data from different data points. Nest used to be quite difficult to get data from, but they do have a published API now. Sorry, let me just do that. So they do have a published API now that you can work with across the Nest ecosystem. So you can pull things like room temperature, maybe when people are touching a thermostat, things like that, so you can get an idea of when they're in. The next one is air source heat pumps. So the ones that we've worked with, the research group the most, are a company called INIVE. So they're quite big throughout the EU. And I'm just going to show you a quick sample of the INIVE data. So you can see that they have this large heat pump. This one, for instance, has got a hot water cylinder buffer in it as well. So there's a lot of data that you can take from this. So just give me a second just to, I don't use WebEx that often. So let me just shift across to another screen, 2 seconds. So again, I don't expect everyone to read all this. It's very small writing on a very big spreadsheet. And the idea of this isn't to do any data analytics, but it's to show you that this is all the data that you can pull just from quite a simple heat pump. So we get things like compressor cycle time. We certainly get the room temperatures. So if we look across the top row here, obviously the time here, we get the outdoor temperature, which is very useful. We get the return temperature on the heating system itself. We get the heat medium temperature. We get the room temperature. We get lots and lots of different things. Okay, we get hot gas bypass. We get everything that we need from a heat pump, but we get those two components, internal and external temperatures. So that's a great bit of data. And we can poll them I think it's every minute or 2 minutes on the INIVE. So, it's a great pool of data that we can have access to. So I'm just going to close that one. I'm going to go back onto my slides. Okay, so yeah, no energy data sort of rating is possible without external conditions. So we can use something like weather comp sensors, which is what the INIVE system was using there, the external air temperature sensor. We can use weather observations if we're forecasting. If we're not forecasting, if we're just taking historic data. We can use forecasting if we want to try and predict days in advance, or we can use building energy management systems, which probably slightly different to what we're talking about today, but many blocks of flats, for instance, and things like this, or district heated systems may have something that you can tap into in terms of outside air and maybe some generic inside air temperatures as well. So just a quick note really about observing data. You saw Yanis there from our research group and Dynastee pulling data in, graphing it, and presenting it in a very rudimentary way. But that's what we need to do. We just because something's smart, it doesn't mean that it's going to give you smart data. It's not going to give you good data all the time. As much as we have problems with sensors dropping off in the old world, smart meters do exactly the same. They can give erroneous readings. The signal can drop and they can go missing for days on end. So just because we might think that something's a modern system, it does have some quite significant drawbacks when it doesn't always work. So we need to look at how we fill in gaps, how we how we filter data, how we clean data. And the last annex that we did, Annex 58, had some really good guidance on that. So I would advise everyone to look at the link there, all about the data processing side of things as well. So how can you start doing this? So it's fairly easy to achieve if you know what you're doing, maybe if you know the right sources of data, and sometimes it might come down to knowing the right supplier and the right people as well. But you're going to have to do some research. It's not something I can tell you how to do it. But what I would say is just be careful with data and GDPR. So we need to make sure that this is very sensitive data, and it's not dissimilar to spying on people. If we have a lot of energy data about one home, temperature data as well, occupancy patterns, then it doesn't take a great deal of imagination to see if that got into the wrong hands, i.e. some criminals, then they know when you're in, when you're out, and this could be used for some pretty nefarious purposes. So we should definitely be careful with it. We should definitely not link it to addresses. We should definitely not link it to people's names and photos and things like this, because that's when things can start to go horribly wrong. So just be really, really careful with this data, and follow all the policies that are in place wherever you are. So just a quick one to finish off with, and I'm regretting doing so many spreadsheets because it's a bit tricky to kind of keep skipping from one to the other. But I just wanted to kind of have a quick wander through some of the other stuff that we do. So it is going to be an energy data revolution. Okay, we're going to get far more data than we can ever handle. EVs, air source, batteries, heat meters, and everything else that comes with them. But if we look at merging one data stream with another data stream, then we can look at doing some quite exciting stuff. So if we look at an EV, for instance, so while I'm talking, I'll give you a quick discussion. While I'm discussing, I'll change over these slides. So I had a very long and laborious discussion with Nissan some time ago. So I drive a Nissan Leaf, and it's great, but I always thought there was probably something more that I could do with it in terms of getting data out of the damn thing at times. It's got an app that comes with it. The app is useless, and it doesn't really give you any kind of sensible data. So again, huge spreadsheet. Sorry about that. But this is my journey home last night. So after Nissan told me that I couldn't get any data out of it, I found out that you actually can, and you can get a hell of a lot of data out of it. And you just need to stick something in the port that's next to the driving wheel. You tie that into your phone. You tie that into Dropbox live stream of every single bit of data that comes off that car. So we do a lot of work with EVs. We do a lot of work with EVs around charging, vehicle to grid, the efficiency of EVs. So how efficient they are to heat up and cool down, things like this. So this is just my journey home last night. So I have about a half an hour drive. So all this data here, and there's plenty more to the right-hand side as well, is the data from just my drive home. So the GPS tells me where I drove. So this is work here, and this is where I live up here. So each one of these points is a GPS point. So, but then it tells me what the state of charge is. So I know how quickly it's reducing. That's really important for when we're doing stuff around vehicle to grid and things like this. As a research group, we're fully on board with the fact now that no house can exist in the future 20 years, shall we say, without an EV being tied to it. So we see the car as part of the home now to start with. It can't be split. Interestingly, for any one of those points in time, I've now got an outside air temperature. So I've got an outside air temperature here, and I've also got an outside air temperature here outside my home. So I might be able to use that for doing HTC work because I've got an outside air temperature sensor parked outside. So I can pull that data and start to use some of that. I can see what the speed is. So I can see where my efficiency might sit on that. Is a good drive home a quick drive, or is it a slow drive in terms of energy? Does the elevation affect it? Clearly does. And the weather affects it as well. So as you'll see, the temperature falls here, but in the winter when you're driving an EV, the efficiency falls off a lot. When you're charging an EV in the cold weather, it falls off a lot as well. If we want to look at weather and we want to look at how moisture affects buildings, which is one of my PhD topics, I can also see what status my windscreen wipers are at. So what, was it raining? If we group all this data into a massive data pool, I'm not clever enough to do this, but we can start to put together a hell of a lot of very, very interesting data. So that's it. So we've gone from smart meters to thermostats to my journey home, and hopefully you found it useful. The big message is, look, there's stacks of data out there. You've got to get to grips with it all. You've got to make sense of it all, but more importantly, you've got to understand it all before you start just to analyze wild graphs that you may not kind of be fully aware of where the data comes from. So I think that's probably me now. So not 5 minutes early, but I'm happy with that. So I'll stop sharing. And I'm now going to hand over to Hans to take any questions, unless anyone's got any directly for me, but I think we'll take it from Hans now.